For the last 2 or 3 days, you've been listening to brominated and chlorinated, and there's no chlorine or bromine in my talk whatsoever today. So if you were expecting some, you'll be disappointed. Heinz asked me to throw a picture in here of my fish, and this was taken last year in Australia at Cairns. I got the opportunity to go out diving, and well, more about him later. We are going to talk about the analysis of fish, but this fish was not harmed in the process. PAH. Simple combinations of benzene, multiple aromatic rings. We've been analyzing in North America for about 30 years on a commercial basis. PAH are made up of multiple rings. You start with the simplest at naphthalene, a 2-ring structure, and you work your way up into the 5- and 6-ring structures with indinopyrene, benzo-GHI. I always state I like my favorite PAH is coronine, which I don't have a picture of here because it's essentially 6 benzene rings in a donut shape, and I like donuts, so. But we're not going to talk about coronine today. About 30 years ago, somebody in the US EPA sat down and said, we've got 16 PAH we want to look at. And those 16 have stuck with us since that day. Whether they're right or wrong, some of them are good, some of them maybe we could care less about, but those 16 are here. You know, I've been doing PAH, I hate to say this, since 1980. When we first started, we did them by GCFID. We'd extract the sample, we'd clean it up. I can remember using a benzene methanol elution on a Cefidex LH50 column. I don't know if any of you still use Cefidex LH50. These days it's usually just extract and inject. But it is possible to analyze PCBs, certainly at the ppm level, on a GCFID. Later, LC came in with UV and fluorescence detectors and improved our sensitivity and specificity. These days, most commercial labs will analyze them on a GCMS. The standard US EPA methods, 8270, 625, 525. There's probably a few others in there. I couldn't remember the LCMS method numbers, but there are a number of them in there. Although in the US, I think if you use an 8270, it typically requires a full scan analysis to get confirmation, absolute confirmation of the mass spectra. Most commercial labs will offer a SIM, a selected ion monitoring analysis. And you know, with some decent cleanup, you can get 1 ppb detection limits in soil and the 10 nanograms per liter that you're required for drinking water for benzo-A-pyrene. Surrogates are added. The methods all call for surrogates, but they are not isotope dilution. All quantitation is by internal standard, meaning an internal standard is put into your solution just before injection onto the GCMS, so you have no idea of losses or no correction for losses that we're so used to when we do dioxins or PBDE analysis. So why go to PCB by high-res mass spec? You know, most commercial labs run what I call at high levels. They're sufficient for government regulations. If I look in Canada, our requirements for most PCBs in soil are in the ppm levels. In water, our lowest requirement is 10 picograms per liter for benzo-A-pyrene. You don't need anything very fancy to hit those levels. You don't need any cleanup. It's essentially an extract and shoot. But about 7 or 8 years ago, we had a major fire in Vancouver in a fish warehouse or a freezer warehouse that happened to be storing a lot of fish. Canadian Food Inspection Agency said, you know, before any of the products that were not destroyed are put out back into the commercial market, they have to be tested for PAH. So several of my competitor labs, all good quality labs, took some samples in and tested them and gave detection limits 50 to 100 parts per billion, said nothing detected, and CFIA said, try again, this is no good. We need detection limits, subpart per billion, down around 0.2 parts per billion before we'll release any of this food. So they came to my lab, and we said, sure, I've done PAH for 30 years, I can do anything on PAH. Well, what were we going to use? As I said, the EPA methods use an internal standard method. Being a dioxin chemist, a PCB chemist, those weren't satisfactory. We wanted to go to carbon-13. You do have a choice of deuterated or carbon-13. Deuterated certainly is more economical, but with D10 fluorine, you've got one of the deuteriums or protons on there which will tend to exchange, and you don't lose the fluorine, but you're going to end up with D9 or D8 fluorine. So when you're looking on the mass spec, all of a sudden it's disappeared. Deuterated PAH elute 2 to 4 seconds before your native PAH. Carbon-13s, on the other hand, elute right below them. Well, it's better than dioxins. There's no 1 second gap. They're usually right below. They're very stable, very easy to use. We went to Cambridge Isotope Labs. They offer a full selection of the US EPA cocktail. They're all carbon-13s, and most of them are C6, but note I've got 2 of them in red there that are not C6. One of them is the benzo-GHI parylene at a C12 and benzo-A-pyrene at C4. It's actually kind of nice because the GHI parylene and indino-pyrene have the same molecular weight at 276. And so having them with a different substitution pattern on there means that one of them is plus 12, whereas one of them is plus 6 from there. So you get two very distinct chromatograms. Although they do separate on most chromatographic systems, this just ensures you got the right identification. Also with your benzo-A-pyrene, it has the same retention time as the benzo B and K fluoranthene. So you have another molecular ion to look at. These are all, one thing I'll talk about later, these 2 are at 99%. Sensitivity is not an issue with PAH. The chromatogram I'm showing here is a 3 nanogram standard, so 3 picograms injected, 1 microliter of 3 picograms. The nice thing, of course, with PAH, unlike dioxins or PCBs, you tend to have a very strong parent ion. It's 90% plus. So sensitivity really is not an issue on the mass spec at all. We went and we're doing some work looking at low level, and I had 12 real-world water samples come into the lab from one of our clients. We adjusted them to pH 10, added 50 nanograms of carbon-13 PAH, did a liquid-liquid extraction with a final volume of 1 mil. You can see in every one of these we had a low-level hit in there. Simple calculations, you take your standard deviation, multiply by 2.81, and you come up with method detection limits, all below 1 nanogram per liter. RSDs, they tend to vary more in the lighter end than in the heavier end, but all around 20% or when we looked at this, I said, great, we didn't spike any of these samples. Those were all real world, but were they really in the sample or not? And we looked, our instrument detection limit was all far below the MDLs we had calculated. But we looked in our blank that we had run with it, and we had positives for everything that we were looking for. And what we were trying to do is hit a provincial water quality objective that you see here on the very right. They wanted benzo GHI paraline down at 0.02 picograms per liter. I told the client, well, we can go down to 1 nanogram per liter, but going below is a little hard because we've got stuff in our blank. And I know I talked to Ben and I said, Ben, your standard's contaminated. I can't go any lower because there's something coming from the blank. So we did a little experiment. We took just 3 solvent blanks and ran those by high-res mass spec. Then we took 3 500 microliter solutions of dichloromethane with 25 nanograms of C13 PAH. And then lastly, we added 25 nanograms of our recovery standard into there. And along the lines, every time we added something, we kept picking up more PAH. Now I operate a commercial lab. I don't have the same fume hood and lab apparatus that Andreas showed us earlier today. I wish I did, and I probably could have better blanks in there. But it shows that the material we're seeing, partially we're introducing it ourselves. Partially, it could be coming from the C13 standard. And lastly, we had a commercial mix for our internal standard or our recovery standard that we added as well, which also was contributing to the PAH. So one of the limitations of going to lower levels is not only within your lab, but in what you're getting. Now, the standards themselves are guaranteed only to 99%, and indeed, we found they all exceeded that standard. So one of the solutions to get a lower detection limit here might be to lower the amount of carbon-13 we add in there, go down to a 5 nanogram solution rather than a 50 nanogram. We haven't taken it that far yet. PAH in tissue. I just want to go quickly over some results here that we did. We are a small lab, an 8-person lab. We're not highly automated. We tend to do things the way we did 20 and 30 years ago, which means for PAH in tissue, we take a 10-gram homogenate of tissue, fortify with 50 nanograms of carbon-13 PAH, add some sodium hydroxide and 100 mils of methanol and cook it for an hour. Following that, we add 50 mils of water into the sample and cook again. I always like to say cook, I like to think of myself more as a cook than I am a chemist, but maybe I'm just a failed cook and that's why I became a chemist, I'm not sure. Before I get to that, I wanted to say we looked at the effect of pH on the pH on PAH. And I was actually a little bit surprised here that we didn't destroy more of the PAH with the acidic solution. We ran at pH 4, pH 7, and pH 12. And really the ones in red are the ones that had the low recoveries. Naphthalene, that could be a volatility issue, but the higher molecular weight indeno, dibenz, and benzo-GHI paraline were low. Also on the carbon-13, these are recovery-corrected data, so if we hadn't recovery-corrected for the carbon-13, they would be lower yet again. But it shows the importance of sticking in basic media. I thought it would be more dramatic, but just the same, run in basic media. The other thing, when you cook fish or you cook meat and you add base and you add water, what do you create but soap? It's a basic formula for soap. And when you try and back extract that, you take that methanol, put it in water, you shake it up, and I tried to get a nice big emulsion when I had the lab do it. When you know the samples we took wouldn't emulsify too much, but you can see a very fine layer in there on top of the water. The hexane's on top, and then you see a fine layer. When you add more water into it, that's how you get rid of soap, is you just keep adding water. You keep 3 to 6 liters of water in there, you'll wash all your soap away, and you end up with a really clean extract out of the fish. No GPC needed, nothing fancy for cleanup. MDLs, 6 10-gram sole fillets spiked. All the MDLs are below or at 0.2 or below. Very good MDLs, met the requirements of the CFIA. We went on to do some alkylated PAH using the same method above. And the alkylated PAH, we use a straight 5-point calibration in there, keeping the native or running the natives from 3 to 300, and the carbon 13s at 50 nanograms per liter or nanograms per mil. We also run a single point calibration for the alkylated PAH, and we only run at a resolution of 3000. There's no sense going to a 10,000 resolution for PAH. We follow that with a single point calibration for the alkylated PAH, and we run C1 to C4 naphthalene, dibenzthiophene, phenanthrene, and anthracene, and then also C1 and 2 fluoranthene pyrenes, benzoanthracene chrysenes, benzofluoranthenes, benzopyrenes. We run all these standards. The alkylated standards come from Chiron, and we used a Phenomenex SVOC column of 30 meters. When I say C4, that could be tetramethyl, could be diethyl, it could be dimethylethyl. You figure out the permutations, but C4 means you've got 4 carbons attached. I don't know if you can see these too well. These are the standards, our single point standards. The top line in each chromatogram is the native, and it follows through with C1, C2, C3, C4, except for the last 3, which just have C1 and C2. Looking at some Alberta crude oil, it's really easy to pick out the patterns in here. Let's see. What I like to do is you can put in a couple of little lines going right down from the parent ion or the parent PAH, and your alkylateds tend to fall within the windows of those ions. So the first line is naphthalene, followed by 2-methyl and 1-methyl naphthalene, then some C2 naphthalene, C3, and C4. As you go down, the absolute intensity decreases and the width of the selection increases. The same thing for phenanthrene, anthracene. We've only got phenanthrene on the first chromatogram, but a doublet of doublets for the second chromatogram, and on down through the list. These are the other chromatograms, dibenzthiophenes, and the rest. So when we go to a tissue sample, this sample was collected out of Burrard Inlet in Vancouver Harbor. About 5 years ago, there was an oil spill there where they dug into an oil pipeline and released oil. And these are taken from crab hepatopancreas. But you can see nicely again the alkylation patterns in there. follows quite nicely what we're looking at. On the bottom chromatogram, everything is scaled to the max, and those last three peaks happen to be dibenzthiophene and the C13 phenanthrene anthracene, so you can't really see the others underneath there. But there's no problem identifying the alkylations that we do see in here. They pop up large as life for you, all the way out to the benzofluoranthenes. The benzofluoranthenes, or the benzofluoranthene benzpyrenes, the top chromatogram is actually benzapyrene, but the bottom ones are more benzofluoranthenes, or alkylated benzofluoranthenes rather than benzpyrenes, because they're a bit too early in the whole elution pattern for that. What we saw, detectable levels in almost all the samples. You know, not most of them were low levels, but still detected. The highest levels coming, in this case here, at our 4-ring and 5-ring PAH. And on to the alkylateds. If you see the natives, chances are you're going to see the alkylateds as well. We're finding it more and more especially in Western Canada, with all the interest in the oil sands, that companies are really wanting to look at the alkylation patterns, not just the native PAH, but the alkylation patterns. And a lot of these are being taken up by tissue, or whether it's avian or fish. We haven't done any mammals yet, and a lot of work on plant-like material. But this method is a viable option for looking at PAH and alkylated PAH in tissue. And with that, I thank you.